The title of this talk is Direction of Arrival Estimation with Magnitude-Only Array Measurements. So magnitude-only means we are taking the absolute value of the measurement. So we don't have the positive and negative signs of the measurement anymore. Here's an outline. So first, we talk about the motivation. So why are we doing that? Why are we taking the absolute value? And then we talk about the associated ambiguities for DOA estimation based on these magnitude-only measurements. And then we develop a fast group sparsity-based phase retrieval algorithm for DOA estimation. And then simulation results and conclusions. First, motivation. So for traditional direction arrival estimation based on antenna arrays, so normally the whole array has to be well calibrated in advance to eliminate possible model errors. And one of them is the phase response error of each antenna. So here, as an example, we consider this N sensor uniform linear array. Okay, this D is the spacing between adjacent sensors, and theta is angle measured from the broadside of this linear array. And then with K incident signals, so big K of them, so without model errors, then the measurements at the pth time instant, so index P, is given by this equation. So XP is the received signal vector, and SP is the source signal vector. And this big A is the steering matrix. So for big K signals, then the steering matrix, this A is N, so big N sensors, so N by big K. So it has big K steering vectors, so A1, A2 until this A big K. So the steering vector for arbitrary direction theta K is given by this. So this is a well-known result. And then for P snapshots, so we have this equation 3. So big X is a matrix, is big N by big P. Okay, and then it's still the steering matrix, and the big S is the source matrix. Now, suppose there's an unknown phase error En at antenna N of the array. So you have big N, these phase errors. So En, N, small n is from 1 to big N. Then in this case, you add this phase error part. So this E, this big E, is a matrix, diagonal matrix, with its diagonal elements given by this E to J En. So it's a diagonal matrix. And then this E to J En, so it's a phase error. So it could be corrected by some array calibration techniques. So, however, it can be eliminated directly without calibration by simply taking the absolute value of each received signal. So you take the absolute value. So this is absolute value, so element-wise. Then basically you have the same, have this new result where you cannot find this error, this phase error anymore, right? You don't have this E anymore. So the phase error has been removed by taking magnitude-only measurements. On the other hand, we could directly design a system which only measures signal magnitude and perform all kinds of signal processing tasks based on such a simplified measurement system. And consider this more realistic case with uncorrelated additive noise. So big N is a noise matrix. Now you have the new measurement is big Y with additive noise and is magnitude-only measurement. And the question is, okay, can we still perform effective DO estimation? So based on these results. So the answer is, oh, yes, we can. So this is actually a classic phase retrieval problem where only signal magnitude is available, or squared signal magnitude. The only difference is okay, in traditional phase retrieval applications, such as optical imaging, crystallography, etc. So there's usually only one snapshot. Like if you have an image, it's just one snapshot. So while in this model 6, multiple snapshots are available. So you can incorporate this group sparsity requirement into existing phase retrieval algorithms and develop a new solution. Okay. However, due to loss of phase information, there will be inherent ambiguities for DO estimation. Okay, this ambiguity for DO estimation means, okay, signals coming from different angles, they give you the same set of magnitude only measurements. And this brings us to this second part of the talk. So associated ambiguities for DOA estimation. So first, one general observation is, okay, if there's only one impinging signal, then there's no way to determine its direction, as the magnitude of array measurement with a single impinging signal will stay the same for all n sensors. So when you take the absolute value, no matter which direction the signal comes from. And to remove this ambiguity, so we can simply put one arbitrary source to a direction of a convenient choice and make sure there will be at least two signals present. So one unknown signal, one known signal. But here, note that we do not need to know exactly which direction this additional source comes from. So this extra signal you put there, you can put it anywhere you like. You don't need to know the direction. Okay. So this is a general observation. So for one signal only. So if you have one impinging signal, definitely you have ambiguity. Okay, there's no way you can find the direction. But for the general discussion, for the further, so more general discussion about ambiguities is very difficult, as they are normally array structure dependent. So we'll use the popular URA as an example to discuss this ambiguity issue. Okay, and then we will introduce two array structures which can avoid this ambiguity problem. Okay, and for URA, so uniform linear array, there are three ambiguities. So first, it's called the mirroring, and then spatial shift, and then spatial order ambiguities. So we will introduce them one by one next. So first, mirroring ambiguity. It refers to a mirrored version, so of the original signals from angle minus theta k would lead to the same magnitude measurements as the original ones. So if you use this x check n as measurements of the mirrored signal, so basically this xn, if you take the conjugate of this xn, you have the same magnitude, right? This conjugate, you put the conjugate into, move this conjugate inside, then you got sk conjugate. Here is a e to minus j n alpha sin theta k, a conjugate. And here, the conjugate means, okay, you have the minus theta k, you have a new signal sk conjugate. So this one has the same magnitude as this original one, but we have a new set of signals sk conjugate coming from directions minus theta k, right? So now you have this ambiguity. Okay, this is mirroring ambiguity. Basically, due to the sin theta term, so this mirroring ambiguity will arise for any linear array structure. As long as it's linear, then it will have this problem. The second ambiguity is spatial shift ambiguity. So it refers to a spatially shifted version of the original source from angle theta k by amount phi over alpha would still have the same magnitude measurements as the original one. So we denote this x check n as the measurements of the shifted signal and theta double dot k as the shifted DOA, then xn, so absolute value xn, so nth sensor signal, then you add this common shift, the common phase shift, and then you can move this common shift inside these brackets, and then you have a new angle. So same sk, same set of source signals, but you have a new angle given by theta double dot k. Okay, you see the whole set of angles, they have been shifted, right, by different amount. So it's a spatial shift ambiguity. This spatial shift ambiguity will not normally affect the DOA order. So if you have a sin theta 1 smaller than sin theta 2 and so on, then for the after shifting, you still have the same result, same order, basically. However, there's another ambiguity, and we call it the spatial order ambiguity. So this ambiguity will change the spatial order of the impinging signals. So with this original order, then after this spatial order ambiguity, this order will change. Okay. So and this ambiguity occurs when applying half wavelength spaced URA to the full angle range, and cannot be solved by placing known reference signals. But it can be avoided by limiting the adjacent sensor spacing to lambda over 4. So if you use linear array, then into uniform linear array, then you need to limit the sensor spacing to lambda over 4, not the lambda over 2, the normal spacing, okay, to avoid this ambiguity. And the analysis for this ambiguity is complicated and is in note here. Okay, for detail, you can refer to this reference tool. Okay. Now, to avoid these ambiguities, okay, associated with the URA, then one solution is, okay, we employ a dual array system. So this is one solution. So it consists of two URAs, where the first one is in the horizontal direction, this one, okay, horizontal direction, while the second has a known angle theta check to the first array, the rotation angle. So due to this non-zero angle theta check, so any shift or mirroring will lead to inconsistency in the two sets of estimated DOA results. Okay, only the true DOA directions you can have a consistent measurement estimate results. Okay. And also to avoid this spatial order ambiguity, you need to make sure the spacing is lambda over 4 or smaller. And another choice, another solution, okay, is to employ this uniform circular array. So the UCA uniform circular array can be considered as multiple pairs of dual arrays, like this one, this one, this one, this one, right? So multiple pairs of dual arrays with two sensors for each subarray, and therefore can overcome the ambiguities issue associated with a single URA. Okay, so this is a general, so uniform circular array. So you have the radius is r, you have a theta signal coming from direction theta, and you have these sensors. And for this UCA, its student vector is given by this. Okay, a little bit different from the uniform linear array case. And then if you can analyze the result, you can see it will not have the mirroring ambiguity and the spatial shift ambiguity. So we can have a quick check here. So for mirroring, so signals arriving from minus theta k generate measurements with the same magnitude from the original ones. The original one is given by this, right? If you add the conjugate here and then add minus theta k, right? And because cosine, so minus minus, you got plus plus. And then you compare this with this, whether you have this conjugate or not, right? These two, in general, they are different. So this is not equal to xn. So you don't have this mirroring ambiguity anymore. And for spatial shift, so the received signals are phase shifted by a specific amount phi n. Then you add this common shift and add it to it, and then you will find out, okay, it's this new version, although they have the same magnitude at the original xn, but because this state is check nk, this one for different sensors is shift for different signals, it will be different. So you don't have a common shift anymore. So although this xn check would share the same magnitude as xn at the nth sensor, this additional shift for the corresponding kth signal at the different sensors are different due to the nonlinear property of the cosine function. So this implies that there's no common shift variable phi n to simultaneously keep the same magnitude as xn and the same shifted angle for all n sensors. So you will not have this spatial shift ambiguity here. But there's another ambiguity for UCAs. For the whole range, minus pi to pi, okay, k incident signals from angles theta k plus or minus pi. So you have a conjugate version of the signal. Also, you add the theta k angle by pi or minus pi, then you will find out, okay, this version is equal to this, and this actually is a conjugate of xn. So you have another ambiguity. So a conjugated version of the original signals from the directions theta k plus pi or minus pi, they share the same magnitude, so give you the same magnitude result. And to solve this ambiguity problem, then we can limit the area of interest to minus 90 degrees to 90 degrees, so half of the whole range. If you limit it to this, then theta k, any theta k plus pi or minus pi, the new value will be out of this range, right? So you can limit the area of interest to this so that you can avoid this ambiguity. Actually, so this ambiguity happens to all two-dimensional arrays, considering the full 360 degrees range. And the URA would suffer from the same ambiguity. So URA, you have the same ambiguity here, but we didn't mention it. The reason is because for URA, the interested angle range is already minus 90 degrees to 90 degrees. So you can avoid this ambiguity, okay, for URAs, because we are not interested in the full 360 degrees. So this is the associated ambiguities. So in this third part, we developed this fast group sparsity-based phase retrieval algorithm for DOA estimation based on these magnitude-only measurements. Now, that's the model. So you have noise, you have the magnitude-only measurement, and then you can use this group sparsity-based method to find this solution to the problem. So basically, okay, you construct for the sparsity-based method, you have a sparse representation, and so you create a much bigger steering matrix. So you don't know how many signals are coming, and so you do the dimension A. Actually, you choose a very big number G. You split the whole range. For example, from minus 90 degrees to 90 degrees, you split the whole range into a very large number, like a number of points. For example, 1,000. Then for each point, it will represent a potential signal direction. And then for each point, each is potential direction, you have a steering vector. And you put all these 1,000 steering vectors together, you form this big matrix, steering matrix A tilde. Okay, so G is 1,000 in this example. And correspondingly, this source matrix S, big S tilde, it will also be 1,000 by P, big P. Okay, so but actually you only have big K sources. Then that means most of the rows of this big S tilde will be 0. So this big S tilde is very sparse. Okay, it's very sparse. So we can use this idea to reconstruct this Y using a sparse S tilde and find the direction. Okay, basically after this reconstruction, all those directions corresponding non-zero valued rows of this big S tilde, they will be the true directions of the source. So this formulation is given by this. So basically, this is the observed, so magnitude only measurement, and this one is absolute value. So you want to reconstruct this Y using a sparse big S tilde, right? And this big S tilde should be sparse. How to say, is a row sparse? Basically, you want to maximize the zero valued rows in this big S tilde, this matrix. So this L21 norm to enforce this sparsity. So L21 norm means, okay, you take the L2 norm of each row of this big S tilde, and then you place all the L2 norms together into a vector, and then calculate the L1 norm. So that's L21 norm. And this gamma is a trade-off factor between the two terms, between reconstruction error and the source. Okay, and this sparsity stuff. so the trade-off factor. And this one is clearly so non-convex, and the problem cannot be solved directly. And the solution we came up with is, okay, we apply this prime technique proposed by this reference 5 to this 15 column by column, and then the non-convex problem can be measured by a surrogate convex function given by this. Okay, in this way, you have a basically you have a convex form. Okay, here is the Hartmann product, and then this problem, this new formulation can be readily solved by the proximal gradient method, and that at the q+1 iteration, this update as tilde q+1 and is given by this. So basically, it's an iterative process, and the mu here is a step size. This delta is a gradient. Okay, and then it has an analytical solution. The whole thing it has an analytical solution given by this. And here just some details. Okay, for the detailed derivation, you can find these details from the reference 2. Okay, it's all attribute access paper published earlier. And then you can have this apply this Nesterov acceleration to increase the convergence speed. Okay, this is all standard standard procedures. And then at the very end, after this acceleration, you have this proposed algorithm called ToyBar. So fast group sparsity based phase retrieval. So ToyBar is the name. And here is a summary of this algorithm. We provided a summary in the published attribute access paper, but we found some small errors there. So this is a corrected version. And now some simulation results. So performance of the proposed ToyBar is compared with the modified G-SPAR based on the dual array structure. And for the modified G-SPAR, 64,000 iterations used. And for ToyBar, iterations fixed at 450 random initializations are used to find the global minimum. And this is a step size. And the angle between the two arrays is 20. And step size 0.5 degrees is used for initial DO estimation. So it's a cos estimation. Then after obtaining the initial DO estimates, then we basically there's a refining step. So a new grade with step size much smaller is formed around these estimated ones from the first step, and then we can refine the estimation result. So there's 2 steps. So when applying the refining step to G-SPAR, the number of iterations is halved as the number of grades decreased, and we have this result. So first, the SNR is 15 dB and 3 signals from these 3 different directions, and the number of snapshots is 20, and sensors is 20. Basically, we have so 2 arrays. So first array 20, second array also 20. And then note that the G-SPAR requires prior knowledge of the number of incident signals, while ToyBar does not. So here you see this is one run of the program. So you see both have identified the directions of the signals successfully, but you see the ToyBar, the accuracy is a little bit higher than this, right? And you can see this RMSE result also give you a similar comparison. So you see this G-SPAR, so RMSE versus SNR, so root mean square error, right? So G-SPAR and this is ToyBar is much better than the G-SPAR. And for the refinement step, so ToyBar is still better than G-SPAR. Okay, certainly the improvement a little bit only here comparing these 2. And then we also have this RMSE versus snapshots. Okay, you see this is G-SPAR, this is ToyBar. So this one much better than this. And this is for the refinement step. So this is G-SPAR, and this is ToyBar. So you see this one also better than this. And in terms of complexity, so here's a running time comparison. So we have different snapshots number, and we compare their running time for these two groups of algorithms. So you see the running time for ToyBar is much smaller than GSPAR. Okay. Basically, this proposed ToyBar, is giving better estimation result and with a shorter running time. Now conclusions. So the non-coherent DOA estimation problem is introduced for magnitude-only measurements of the received array signals, which is therefore robust against phase response errors of the array. The inherent ambiguities for DOA estimation associated with magnitude-only measurements are discussed in detail with the URA as a representative example. And two structures are provided to tackle the ambiguities issue, including a dual array structure and the UCA, uniform circular array. So the non-coherent DOA estimation problem can be formulated as a group sparse phase retrieval problem and solved by the proximal gradient method after transforming the original non-convex cost function into its convex surrogate via the prime technique. And the proposed ToyBar outperforms the existing modified GSPAR algorithm as demonstrated by computer simulations based on the dual array structure. And here's a reference, the most related reference to this talk.